Hello. Hello, I'm Dr. Natalie Whitcomb, and in this PowerPoint, I'd like to explore with you the dynamics and morphology of barrier islands, and in particular, Honeymoon Island State Park, which is a barrier island off the Gulf Coast of Florida. This is part of the virtual field trip to Honeymoon Island State Park, and in addition to this PowerPoint, you should watch the videos by Dr. Douglas Elmore, as well as the videos that have been made by our Polk State College students about previous field trips. Barrier islands are long, narrow, sandy islands that typically parallel passive margin coastlines or trailing margin coastlines. Elevation-wise, they're usually 5 to 10 feet above sea level. This is an example of a classic East Coast barrier island. It is Assateague Island that is found off the coast of both Maryland and Virginia. If you look at the map on the left, you can see its location. On the right side of the slide is an aerial photograph of Assateague, and you notice that there's a sandy beach that faces into the open ocean. This is the Atlantic Ocean. And then on the back side of the barriers are separated from the mainland by a back barrier lagoon or back barrier bay. And the side of the island that faces the bay is vegetated. This is usually some sort of marsh. Further north along the East Coast, it'll be a grass marsh. In our part of Florida, south of Cedar Key, our back barrier marshes are typically mangroves. The ocean side of the island experiences much higher wave energy than the back barrier side. And we'll explore more of this later on in the PowerPoint. This is Honeymoon Island State Park that we will focus upon. It is just to the east of Dunedin, Florida, about 2.5 miles from where we are. I'm sorry, 2.5 hours from where we are. It's connected to the mainland by a man-made causeway. And if you look at the island, the portion where the green arrow is amazingly rectangular. This is man-made, and the island is separated from Caladesi State Park by a small inlet. Okay, so barrier islands are separated from each other by these inlets, and the inlets move and the islands move. So we'll take a closer look at this now. Okay, so the question is, how do barrier islands form? And depending upon where you are, they may form in different ways. The long, narrow islands that parallel our East Coast are thought to represent ancient dunes and beaches, or we sometimes call them beach ridges, that formed during the geologic period called the Pleistocene. And at the end of the Pleistocene, we were in a glacial period, and sea level was much, much lower than it is now. And so our beaches would have been to the east of where they are now. As sea level rose, these beaches became stranded from the mainland and began what would be our barrier islands. Now, along our Gulf Coast, our barriers may have had a slightly different mechanism of formation. The rock here is limestone, and the surface of the limestone dissolves very easily when it's exposed to rainwater, to salt water, and so it becomes very uneven and sinkholes form where the limestone collapses. And so our barriers may have begun as sand that accumulated in the irregular surface of our limestones. Okay, so if we take a look at this image, this depicts how our East Coast barriers are supposed to form. So if you look at the uppermost picture, you can see this is a lower stand of sea level. We have a beach ridge, which is beach and sand dune complex. And then in the middle, the sea level begins to rise. The beach ridge becomes cut off from the mainland by a lagoon or back barrier bay. And the side of the barrier that faces the ocean experiences higher wave energy, and so it begins to erode. But on the quiet lagoon side, sediment actually accumulates. And so with rising sea level, as you can see in the lower image, with rising sea levels, these islands begin to migrate, and they migrate towards the mainland, which is exactly what we see our barriers doing today. And so this is an idealized cross-section of a barrier island. You see the offshore, and then as we move onshore, there's a series of bars separated by low areas called troughs. These bars will migrate with wave action towards the ocean side of the island. As waves approach from the open ocean, they begin to drag bottom, and this wave action will move sand up the ocean side of the bar, and it spills down the island side, and the net result of this is the migration of the bar towards the island. These bars eventually will reach the island, particularly during the summertime, and become part of the beach. And this is a way that sand is replenished on these islands. The intertidal is the area between high tide and low tide. The rack line, this is the line of seaweed and marine debris on the coast that's usually stranded right around high tide, maybe a little bit higher, and it represents the highest tides and the highest extent of waves breaking on the coastline. And then there's what's called the berm crest. This is an erosional crest associated with the inland extent of erosion. The flat area behind it is called the berm. At the back of the beach, then we have sand dunes, and we may have more than one set of dunes. Primary dunes are 4 dunes, which are the active dunes. And then behind them, secondary or back dunes, which are now inactive. And in the low areas, interdune grasslands or meadows and forests or sometimes boggy areas will form. And then the lagoon side of the island experiences much lower wave energy, and so there's usually a tidal marsh there, either grass or mangroves. And then lagoonward of that, in the intertidal, there may be mud banks or mud flats that are exposed at high tide and flooded at low tide. Here we have a bird's eye view of the parts of the barrier island that were shown in the previous slide. So you can see what they look like if you were looking down from above, the bars in the near shore, the berm, the dunes. The one thing that is different here is there's something called an overwash fan. Overwash fans form during very bad storms or hurricanes. And what happens is the storm surge and the storm waves will either overtop the dunes or will erode a channelway through the dunes that allows floodwater to spill into the interior of the island, bringing with it a lot of sand. when the floodwaters recede, this sand is left behind as a fan-shaped deposit called the overwash fan. Overwash is important because it is one mechanism for adding more sand to the island, and it is also a mechanism that facilitates the migration of the island towards the mainland. And then if you look at the marsh, you can see that it's divided into a high marsh and a low marsh, and this has to do with the tidal range and the types of plants that are found in each area. And this is an actual aerial photograph of a barrier island showing the foreshore with the bars, the beach, the dunes, and you can see what an old overwash fan would look like. Now, this slide depicts what our barriers on the Gulf Coast of Florida look like. If you look at the little box in the lower left-hand side, that's a map. You can see Tampa Bay, and you can see the location of each one of these images that's on the right side of your slide. The A corresponds with the A image. Now, these are cross-sections, or a view of what it would look like if you could see down beneath the surface. They're made with a ground-penetrating radar. And what this piece of equipment does is it basically sends a radar signal, sound down into the subsurface. And wherever there is a change in the density of the rock or the sediment, signal is reflected. It's picked up with a receiver, recorded, and then it's usually processed with a computer, and the image is what you see. And so the dark lines here represent density changes that reflect the sound waves, and this typically will parallel the subsurface geology. So you can see the top of the limestone and what that looks like, and how the thickness of sand correlates with irregularities in the limestone, which could have led to the formation of our barriers. And so as we look at it, Three Rooker Bar is immediately north of Honeymoon Island, and Caladesi Island is immediately south. And you can see how the barriers seem to correlate with high points in the limestone. And here's an aerial view of Honeymoon Island, which we're going to talk more about. So as you look at this image, you can see to the right-hand side the road, and this is the causeway that goes to the mainland. It is man-made, and then the more rectangular part of the island with buildings on it that are man-made. You see down to the left, there's the inlet, and on the far left side of the photo, you can see the north end of Caladesi. This inlet is it's called Hurricane Pass. There's large sandbars within the inlet, and these represent the flood and the ebb delta. The inlet is kept open by constant dredging by the Army Corps of Engineers. And then as you look in the upper right, you can see a long sandy area of the island that's separated by a little lagoon from a vegetated area. This area represents a sandbar that became part of the island, and cut off this lagoon. And the vegetated area is the original part of the island. So if we take a look at the near shore and the offshore and the near shore features of barriers, and go to the next slide, you can see that in most cases, you can see the near shore bar here that's separated by a trough from the beach. This is taken at low tide. And so when the near shore bar becomes part of the beach, we call it a swash bar. And it's separated from the beach by a channel called a runnel, and there's a channel called a rip. At low tide, these bars are exposed. They're flooded at high tide, and when the tide goes out, the runnel and the rip accommodate the water flowing away from the coastline. Now on the next, we see an example of a swash bar with a well-established runnel, and this is on the north end of Clearwater Beach. Now on the next slide, we'll talk about the beaches. The beaches of beaches are always in motion. Barrier islands are always in motion. Their beaches are always in motion. The sand is being moved by waves, by tidal currents, by a current that often parallels the coastline called the longshore current, and the wind is also moving it around. So on the next slide, we see a cross-section of the beach. We've seen this before, where you can see the longshore bars, the beach face, which is the intertidal. There's two berms on this diagram, and on many beaches you will see two berms. It depends a lot on the climate. The berm that is closer to the ocean is often called the summer berm. And this berm crest represents the highest extent of tides and waves during the summertime. Now, in many places along the East Coast, the wave energy tends to be lower during the summer. The storms tend to be fewer and further between and not as violent as the winter storms. And so the summer berm is often a lower energy situation. The sand may be slightly finer grained. And then the next scarp separates it from the berms that are immediately adjacent to the dunes. And this is sometimes called the winter berm. The winter berm, this represents the extent of winter storm waves and sometimes hurricane waves. Many times the sand will be slightly coarser on the winter berm, and you may see a lot of dark colored sand. What makes the sand dark colored are what we call heavy minerals. And heavy minerals are typically composed of metal oxides, oxides like iron, titanium, those sorts of metals. There may be some garnets mixed in because garnets are iron-bearing minerals. And in our case here in Florida, some of this will be phosphate. And then at the back of the beach are the sand dunes. On the next slide, this is a view from 2007 or 2008 of the beach on the south end of Honeymoon Island. And the one thing you'll note is the beach is fairly flat. So this is a lower energy beach. You can see a lot of rocks on the beach. These rocks are pieces of limestone, and the way that they got there is they were actually quarried or dug up offshore by a person who wanted to develop the island and put a housing development out there. And the plan was to make the island bigger so they could build more houses by filling in areas with this limestone rubble and then covering it up with sand. Wave erosion, though, has continuously uncovered this, and it's pretty much permanently stuck on the beach. Now, if we go to the next slide, this is just north of the north parking lot on Honeymoon Island. And if you look at the date, you can see that it was taken in 2008. So what's interesting here is you can see an erosional scarp right next to basically the beach face, which is the intertidal, and then there's an erosional scarp. You can see the line of seaweed, that's the rack line. Then you have a berm, and the beach here is a little bit steeper, so it's a little bit higher wave energy. And at the back of the berm, there's some trees, and these are mangroves. Mangroves are typically found on the back barrier or around lagoons or ponds, those sorts of features. So what's happening here is erosion on the Gulf side has caused the island to migrate out from beneath these mangroves, leaving them stranded. Since this photo was taken, these mangroves, basically erosion caused them to fall into the Gulf of Mexico, and they died. The trees have all died. And see on the then you can see the sand that's been piled up here. The dunes have been lost in this area, and on the other side of this sand is the end of that lagoon, which is a little pond that we'll take a look at on a later slide. And so these are stranded mangroves and it shows how fast the island at times has migrated. On the next slide, this is looking north from where those mangroves are at the north end of the island in 2008. You can see the beach face with the little erosional scarp, and there's two rack lines. And the flat area is the berm. The beach is slightly steeper here. And so this is a higher energy beach. What you can't see here is that immediately offshore is the area where that limestone was dug out. And so this is an area of much deeper water. Typically, as waves approach the coastline and begin to drag bottom, some of the wave energy begins to dissipate. However, in this case, because of that old quarry there's deep water very close to the beach, and so higher energy reaches the beach, and this has caused problems on the north end of the island with continuous wave erosion. Another interesting thing here is in the fall of 2008, early in the fall, we had a tropical storm, and that second rack line that is further inland represents the waves from that storm. So in the next slide here, we'll take a look at the sand dunes. And if you've been to other beaches on the east coast of Florida or further north, you'll notice that these sand dunes are fairly small compared to sand dunes that you see elsewhere. The issue here is there is not a huge sand supply on our Gulf Coast. You may remember from reading in your textbook the term relic sand, or sand that has moved into an area by a process that is no longer continuing. And so our sand along the Gulf Coast, south of Cedar Key, is what we call relic sand. It came here in the Pliocene and the Miocene, which was 15 to 30 million years ago. And what was happening at that time is the Appalachians mountains to our north had eroded away to the point where they no longer balanced in the mantle, and so they rose isostatically. And when this happened, it was not an overnight process, it was a very slow process. And as it was happening, the streams and the rivers draining out of the Appalachians began to flow a lot more quickly, and erosion began again in force. And this stream erosion carried sediment from the Appalachians down to the Gulf of Mexico, where it was moved, it was spread to the south by tides and by currents. Since then, the Appalachians have eroded to a point where we are no longer getting any new sediment from the Appalachians. So the terrigenous sediment that we have here is all that we will ever have here. And as a result, most of our sediment, or the sediment that's being made now, is biological, fragments of shells and that sort of thing. And so we don't have a big sand supply, which means we don't have very large dunes. But what the dunes do is extremely important. Dunes store sand. And during storms and during periods when the wind is strong, sand is mined out from the dunes by storm waves and wind and spread back out on the beach, naturally replenishing the beach. The dunes are also a barrier that tend to protect the inland parts of the island from storm waves. And the dunes are held in place by the plants that grow on them. That's why we're not encouraged to walk on the dunes. These grasses that you see, these are sea oats, and they're an endangered species. But what their roots look like beneath the sand is they are tough and they're tangled, and they hold the dunes in place. If we lose the vegetation, then the dunes will begin to migrate with the wind, and they can migrate inland. Now on the next slide, we go back up to just beyond the north parking lot, and we see what's called a little cat's eye pond. And this is the end. If you think back to the aerial view of Honeymoon Island, this is at the end of that inlet between the beach and the vegetated area. And it's a little tidal pond. The trees behind it, you see, are mangroves. There are lots of crabs and fish that live in this area. And the sand that you see here is actually part of an overwash fan. So on the next slide here, we take a look at the grasslands or the interdune meadows. And you're looking towards the Gulf of Mexico. And you can see the primary dunes along the Gulf and hints of secondary dunes and all of the grasses that grow in this area and the succulents. So this is a highly productive area. As we look at the next slide, we see what's called a maritime forest. And what's important about this is along this portion of the Gulf Coast, this is the last vestige of maritime forest that's been preserved. The pine trees that you see are native pines. On the other barrier islands, which have been developed, we have lost this forest. So it's a very important feature because it's preserving our last maritime forest along this section of the Gulf Coast. And then on the next slide, we take a look at the back of the barrier that faces the lagoon. And this is a mangrove swamp. You can see, if you take a look, that there really isn't much wave action. And the water looks rather muddy. The back barrier lagoons tend to be much lower wave energy than the beaches that face into the open ocean or the Gulf. The plants here, as you can see, that you have the mangroves, and you can see their air roots. As the tide comes in and goes out, the physical presence of the plants slow the water down and trap the sediment. So the island is actually adding sediment on the back barrier as the portion of the island that faces the Gulf or the ocean is experiencing wave erosion. The other thing that's important back here is that mangrove swamps are incredibly productive and support a huge diversity of life. Lots and lots of fish will spawn in the mangroves because there are places where the baby fish or the spat can hide. and avoid predators. There are lots of birds that will live here or hunt here or feed here. And oysters live here immediately out in the lagoon at low tide. There are mud bars or mud flats which are exposed at low tide and covered at high tide. And these support huge populations of burrowing animals, like different types of clams and worms that will filter feed or feed on the organics in the mud. And then beyond that, we have grass beds, usually something like manatee grass, which are also extremely productive. And like the mangroves, the grass beds are nurseries for many different types of fish. And so a lot of the fish that we enjoy fishing offshore, the big sports fish, are dependent upon these environments as their breeding grounds and their nurseries. Okay, so on the next slide here, we're going to take a look at how barrier islands move. Barrier islands are not static, they're dynamic, and they are always in motion. They are moving with the tides, with the currents, with the waves, and with rising sea level. So on the next slide, we take a look at overwash. And overwash happens during storms, winter storms or hurricanes, depending upon where you are. And what happens is during these storms, the storm surge will either overtop the sand dunes, which means that the storm surge is vertically taller than the sand dunes are, or because of the force of the storm surge and the storm waves hitting the coastline, it will actually breach the dunes or erode a pathway through the dunes, allowing floodwater to flow into the interior of the island, carrying a lot of sand with it. And then as the storm surge subsides and retreats, the sand is left behind as a fan-shaped deposit called an overwash fan. And as we mentioned before, this is one of the mechanisms that helps barriers migrate towards the mainland, and it also replenishes some of the sand on the island. Now on the next slide, we see an aerial view, which you've already seen before, where you can see the remnants of an old overwash fan. Then as we move to the next slide, this is an aerial view of Three Rooker Bar, just north of Honeymoon Island, about 10 years ago. And you can see, if you look on the lagoon side, an overwash fan. Now on the next slide, we'll take a look at how sand moves parallel to the beach. So many times the waves approach the beach at an angle. They are head on. And as they break, what they do is that the water runs up on the beach carrying sand with it. And then the water finds the straightest path back to the ocean or the Gulf as it flows backwards off the beach. And it carries sand back with it, and then the next wave will come in at an angle, carry sand up at an angle on the beach, and drain straight back into the ocean or the Gulf. And the net result of this is that sand is moving parallel to the beach. And this sand is called either beach drift or longshore drift. Drift is a term geologists use to refer to any type of sediment that is moved predominantly by one process. For example, wave action along the beach. Longshore currents, which are currents parallel to the coastline, can develop, and these will also transport sand parallel to the beach. And on the next slide here, you can see, this is from Honeymoon Island, you can see an example of how the waves approach the beach at an angle. And these are fairly low energy waves. They're not very big. Oh, and then so if we go to the next slide, this is a summary of what we've been talking about. The breaking waves carry sand up on the shore, and then offshore, longshore currents transport sand parallel to the beach. The waves transport sand parallel to the beach. And if the transporting mechanism, such as a current, slows down, sand will be deposited. Now, because barrier islands are always in motion, we build buildings and roads, and we've urbanized barrier islands. We've made parks on barrier islands. We try a series of different strategies to try to keep the islands in one place. If you've built a house on an island, you are not going to be terribly happy when that barrier island migrates out from beneath your house during a storm, or when your beach that was, say, 10 feet wide is reduced to 2 or 3 feet by wave erosion. And so we use a variety of engineering and non-engineering methods to try to keep barrier islands from migrating too rapidly, and coasts in general from moving too rapidly. Look at the next slide. Some of the engineering strategies that we use are groins, jetties, seawalls, and we can use direct replenishment, which involves putting sediment or sand directly on the beach. On the next slide, we see an example of groins. Groins are low walls that are built perpendicular to the beach, and what they do is they disrupt the longshore transport of sand, causing sand to be deposited on the upcurrent or the updrift side of the groin, and yet that causes some erosion on the downcurrent or the downdrift side of the groin. So the issue is that once somebody builds a groin, they have they trap sand, they have a beautiful sandy beach. Their downdrift or downcurrent neighbor will begin to experience more erosion. So then the neighbor builds a groin, and it's self-perpetuating. You end up armoring the entire beach with groins. And the groins can be made out of wood, they can be made out of concrete, they can be made out of just, rock rubble. Some of them now are made out of recycled plastic. So if we look at the next slide, you have an aerial view of what happens when you begin to build groins. And if you look, you can see that the updrift side is towards the bottom of the photograph, and so the longshore drift is flowing from the bottom towards the top, and so you can see that sand is trapped on the updrift or upcurrent, and there's erosion on the downdrift or the downcurrent. But you'll notice as you look at the photograph that with each successive groin, there is less and less sand being carried along to be trapped. So this is the problem with groins. The next slide depicts jetties. Jetties are walls that are built to stabilize inlets. Now, the thing about barrier islands are separated from each other by inlets. And as we mentioned, inlets will migrate. And the migration can occur in different ways. With the net transport of sand, a lot of times sand will accumulate on the upcurrent or the updrift side of an inlet. But the inlet allows the tidal flow to go in between the island. And so you still have the flood tide coming in and the ebb tide coming out. And as sand builds up on the upcurrent side or the updrift side, the tidal currents will tend to erode the down current or downdrift side of the inlet, causing the inlet to migrate. The other thing that can happen is during major storms. If part of the island is narrow and the island overwashes, new inlets can break through due to storm erosion. And sometimes deposition during storms will fill in inlets in one place and new inlets will open up in another place. And so when we build things like roads and bridges, we don't really want the inlet migrating out from under it. And so we stabilize it by building jetties. And the next slide depicts direct replenishment. When we directly replenish the beach, sand is either mined from offshore bars or brought from sand mines inland. Offshore bars, what's used are usually heavy equipment mounted on a barge, such as a drag line mounted on a barge, and the sand is put into hydraulic pipes and moved on shore, where it's spread around by heavy equipment. And so this is this picture is one of the early replenishment efforts of Honeymoon Island. The major issue with direct replenishment is it is expensive. And typically the sand will not last forever. Sometimes within 2 to 4 years, normal erosion has already removed the sand from the replenished beach. So if we look at the next slide, we'll take a look at the history of Honeymoon Island and the history of its direct replenishment. So if we go back in the past, originally Honeymoon Island and Caladesi Island were all one island, and it was called Hog Island. And prior to the 1920s, there were some people who settled on Hog Island and farmed out there. Now, in the early 1920s, a hurricane came directly up Tampa Bay. And this is the last time that the eye of a hurricane has come right up Tampa Bay. When this happened, Hog Island, as it was called then, overwashed. And Hurricane Inlet broke through, separating it into Honeymoon and Caladesi. Now, the reason Honeymoon got its name is it became a destination. It was considered a romantic destination for honeymooners. Someone built little cottages out there, and you could go out there by boat, and it was considered a place to get away during your honeymoon. And then when World War II came along, it was also used for rest and recreation, or R&R leave, for troops on leave, and for people who worked in the war effort, such as in munition factories and that sort of thing. Now, if we move up to the 1950s and into the early 1960s, there was a building boom along the east coast of the United States. And we began to develop coastal property at a very rapid pace. And we began to develop the barrier islands. People love living on the coast, and they love vacationing on the coast. And so developers began to buy up property on barrier islands and develop them. Honeymoon Island was purchased by a developer in the 1960s. He began to mine limestone offshore, off the northern portion of the island. And what he wanted to do is he wanted to fill in the island and make it wider so he could build more houses there. He built the causeway. He built that little rectangular portion that you've seen on the aerial photographs. He ran sewer and water lines out there. And because of that deep water immediately offshore from the northern portion of the island, and the change in the shape of the island, this has exacerbated the erosion problems on the island. But, we see this with 20/20 hindsight. So then what happened is people in Tampa, particularly one of the garden clubs in Tampa, the members of the garden club began to think about how we were losing all of our undeveloped barrier islands, and that this developer was not very far along in the process, and that Honeymoon was really one of the last undeveloped barriers off the coast of Tampa. And so they began an effort lobbying the legislature to buy Honeymoon Island and preserve it. So if we move to the side, you can see that the state of Florida bought up Honeymoon Island between 1974 and 1982. Some of the dunes have been lost, so they built the parking lots. They tried to restore the dunes. And when you lose your sand dunes, one of the outcomes of this is beach erosion becomes much worse, because remember we talked about how the dunes store and release sand to the beach. So in 1989, because of beach erosion, the first replenishment took place, and 280 cubic yards of sand was placed on the beach. This sand was actually mined inland. Some of it came from Polk County, and a lot of it was stained orange with iron stain. If you look at some of the dunes, you can still see remnants of that sand. And by 1991, the island was eroding away again. So 2007, 2008, there was another replenishment effort, and 140,000 cubic yards of sand was placed on the island, and what's called a T-groin was constructed. So what a T-groin is offshore there's a low wall that parallels the beach. If you look in your book, it's just like what's called a breakwater. And its job is to absorb wave energy. And then that low wall is connected by basically a groin to the beach. And the groin's job is to trap sand that is being moved with the longshore current and the longshore drift. And so you're doing double duty here. You're building a structure that will absorb wave energy and will trap sand moving parallel to the coastline. So go to the next slide. This is an aerial view of the first replenishment, and you can see here there's an offshore barge, and they are mining sand on the barge, and then it's put into, the sand is mixed with water, it's put into a hydraulic pipe, and it's blown on shore. On the next slide, we can see what happened to the sand after that first replenishment area. So this is 2009. And most of the replenishment sand has been eroded away. The limestone, if you look at the picture on the right, the limestone rubble is exposed on the beach by wave erosion. And on the left, this is a bathhouse at the north parking lot. You can see the curb, the remains of the north parking lot. And wave erosion has completely undermined this bathhouse. Ultimately, the bathhouse, they moved the bathhouse to the back of the parking lot so it wouldn't collapse into the Gulf of Mexico. And sandbags were placed along the edge, the Gulf side of the north parking lot to try to stop the wave erosion and stop the parking lot from crumbling into the Gulf. So if we go to the next slide, we move up to the latest replenishment effort. Now remember, it takes a long time to plan these replenishment and do the studies that you need, and so that's part of the reason for the gaps. In 2015, the most recent replenishment effort put 165 cubic yards of sand on the island and built 3 more T-groins off the north end of the island to protect the beaches just off the north parking lot and a little further north. In this area, a lot of the dunes have been lost, and so a dune restoration is also planned. Now, the next slide shows the replenishment effort that's going on. You can see the large pipes. These are parts of the hydraulic pipes that are used to transport sand onshore. The sand was mined from offshore bars and blown onshore as a sand water slurry. And then on the next slide, you can see the beginnings. This is in the summer of 2015. The beginnings of the new T-groins. And so this is the breakwater portion that you can see right offshore that has been built, and then a groin will be built from that to the beach. And the slide shows sand being pumped onto the beach. You can see the slurry being blown out of this pipe and the heavy equipment that's being used to move the sand around on the beach. And on the next slide, this is sand being moved around, and this is the 2015 replenishment effort. And so the result now is, which you'll see in some of the other videos here, is the beach has been replenished. 3 new T-groins, so there's 4 T-groins total, have been built to protect the north end of the island. And hopefully this will keep the sand in place for a number of years. But as we know, as we've talked about, these islands are always moving. We can slow down the movement, but ultimately we may not be able to stop it. The last slide is sunset over Tampa Bay, the back barrier, and I hope you've enjoyed this brief tour and history of Honeymoon Island.